Da casa si vede, si sente?
Sì, prof.
Ok, grazie. Allora cominciamo. So last time I think we started with the Grand Canonical Ensemble, just to set up some of the previous equations. Just a summary, Grand Canonical. Do you see what I'm writing? Maybe not, right? It's not even focused. Si vede, mi sa.
No, prof, è molto debole il pennarello.
Let's see this one. Okay, maybe with blue, maybe it's better. Okay.
Yes.
Okay, so here it's with the Grand Canonical Ensemble. Now the equations that we need to remind, that I need to remind you are the following. First of all, the Grand Canonical Ensemble, which is the distribution function, which depends on n, not the total number of particles and total energy of the system on which we are focusing. And this is equal to E to beta. Here we have the ground potential plus mu n minus E, where n and E are functions of the coordinates and the momenta of the particles that we are considering, whereas omega is the ground potential. And this is a thermodynamical function, so it does not depend on the coordinates and the moment of the particle. But if you want, it's a normalization, it's a sort of normalization of this function. Indeed, the ground potential is related to the Grand Canonical partition function by this equation. So this is the Grand Canonical partition function. And is provided by E to minus beta omega, where omega is the ground potential. In this way, basically, when I integrate over number of particles and over all the coordinates and momenta, basically this is indeed a distribution function in the sense that I get 1. So it's correctly normalized to 1. And another quantity that we at some point introduced was the fugacity, which is E to beta mu, and this is the fugacity. I think it's visible. And what we obtained last time, and similarly to the case of the canonical ensemble, in which the internal energy is just the average over the ensemble of the energy of the system, and was derived as a derivative with respect to beta with a minus of the logarithm of the canonical partition function. Now, in this case, the number of particles is not fixed. It can fluctuate, and in principle, I can compute an average and the fluctuations, so the variance, if you want. And the average was computed as follows. Well, actually, we have computed it, but it can be obtained by just using the simple formula, which is fugacity Z derivative with respect to Z of the logarithm of the Grand Canonical partition function. Okay, I think that this was derived last time. Well, this partition function, which was written here, is a function of the thermodynamical variables, which in this case are, if you want, Z, fugacity, which contains in turn the chemical potential, the volume, the principle, and the temperature. So it's a function of those variables, which are macroscopic variables, so thermodynamical variables. And basically that was it. Then, yeah, okay, then at some point they stop there. Io devo cancellare questo. So then we said that if I compute twice this derivative, so if I act with this operator, what we did last time, you still see it? Forse sì, così.
Più o meno sì.
Più o meno sì. No. Io andrei dalla portineria e direi, ma provate a scrivere voi questi pennarelli. Mi dà sempre la stessa storia. So this is, let me try with the red, try two colors, but they are not working. I will try with this one. And then what we derived last time, that this is basically the variance. So it's the average of n squared minus the average of n squared. This was derived last time, okay? Now, what I'm going to show is that basically this fluctuation, as in the case of the canonical ensemble for what concerns the energy, is actually very small. Well, it is actually vanishing, at least in the thermodynamical limit. And if I do not have any, let's say, peculiar behavior of our system, which is, I will discuss this a little bit today, what we have in presence of phase transitions, okay? But in normal situation, this fluctuation will go to zero, as you will see in a moment. Indeed, what is Z is e to beta mu, from which the log of Z is equal to mu, and here I put 1 over beta, and therefore the derivative with respect to Z can be written as derivative of mu with respect to Z, derivative with respect to mu, and derivative of mu with respect to Z is 1 over Z beta, derivative with respect, and then derivative with respect to mu. And if I multiply this by C, so therefore this operator, if you want, is just 1 over beta derivative with respect to mu. Therefore, I can write this as follows: n squared average minus n average squared is twice this operator, which means kBt squared times the second derivative with respect to mu of the log of the partition function z of g. Okay, so let me now divide by the volume of the system squared. And let me just put, you will see in a moment why, a volume here and the volume here, where V is the volume. Now, what is this quantity? M divided by a volume is a density. So this is the density fluctuation. So if I introduce N, which is the density, which is the ratio between N and V, this is basically the fluctuation of the density. So N squared average minus N average squared, since the volume is fixed. So this is the density fluctuation, or the density variance fluctuation. And this density fluctuation is equal to kBt squared divided by the volume. And then I have a second derivative with respect to mu squared of the log of the partition function divided by the volume. Okay. Now we will compute this quantity later, but actually here what I can say already is that basically this quantity must be finite in the large N and large B limit. So this is a finite quantity. In the thermodynamical limits. What is the thermodynamical limit? Is the one in which N goes to infinity. I remind you what is this. The volume goes to infinity, but the ratio between N and volume is finite. Demonto anche questo. Sorry for that. I will go downstairs to see if they have another type of call. Now, let me comment now on this. Why I'm saying that this quantity is finite? Because this function z of g, it was e to minus beta omega, and therefore the log of this quantity is equal to minus beta omega. And now I can see that this is an extensive variable because it was summed to the energy and to the mu times n. So this is an extensive variable. And therefore, we know extensive variable because remember it was, I had at some point omega plus mu n minus c. If those are extensive, also this quantity is extensive. This was in the Grand Canonical Ensemble. Therefore, it must scale as the total number of particles. So the log must scale as n, and therefore the log of z of g scales as n. This is the volume, and therefore the larger in the thermodynamical limit it is a finite quantity. Whereas, of course, here I have a suppression due to the volume instead. Okay, so therefore, so this is the thermodynamical limit. The volume is going to infinity, and therefore I can conclude that the density fluctuations are also suppressed in the thermodynamical limit, like 1 over v, unless we have some pathology that we will see later. So in normal condition, the conclusion that the fluctuations are suppressed as 1 over v, fluctuation of the density, yeah? As 1 over v over the volume in the thermodynamical limit. Okay, so the situation is similar to the situation of the canonical ensemble, in which we have shown at some point that the fluctuations of the energy are suppressed, at least in the thermodynamical limit. Now, we will see later that actually this is correct if no phase transitions are here. And you will see why later. If no phase transition in the case of phase transition, in particular second order phase transition, this is not true anymore. Okay, now let me see what I'm going to do. This and this. Okay. Now, basically, what I'm going to do is to provide a proof that the grand canonical, the grand potential, sorry, is nothing new actually. It's just the product of the pressure times the volume. So it's a quantity that we have already seen. And also we would like to see if the typical case of the ideal gas in the grand canonical ensemble, we recover the usual formula. So first thing that I want to do is the following. When I compute the logarithm of this function here, I have to do, by considering the definition of the grand canonical partition function, I have the logarithm of a sum over m and integral over dq and dp, so an integral over the phase space. So I have the sum of n0 2 plus infinity, and if you remember, there was a z to the power of n, the fugacity to the power of n. Then I have to integrate over dp dq e to minus beta e, where also dq and dp, of course, depends on n, because if I have n particles, I will have 3n values of momenta and 3n values of q. Since I'm changing the number of particles here, I also, the dimension of this integral will change. Good. Now, what I'm going to say is that this is almost equal if fluctuations of n are suppressed. What I can say is that n is almost equal to its average. Similarly to the case in which the internal energy is the average of the energy, if the fluctuations are very much suppressed, which is true in the thermodynamical limit. And therefore, this sum here will be dominated by this term here. Because when I move from the average, I have very strong suppression of the possibility to have another value of n at fixed chemical potential. Okay. Remember that this is always the situation as the one that we analyzed for the system, the lattice of spins, in which we said that there is the maximal entropy configuration was overwhelmingly more probable than the other. So once you move from the maximum entropy situations, the probability is very, very small. And here is similar, which is also similar to the case of the canonical ensemble when you consider fluctuations of the energy. So basically now I can assume that basically this n, the sum, is just dominated by just the average of n, okay? Instead of summing, I will just consider the value n equal to average of n. Therefore, it's equal, almost equal, the logarithm of z to the power of average of n. And then, okay, this is similar to this case, so to the previous case. Here, of course, this depends on the average of n, minus the beta e. Okay, now this is equal the logarithm, everything here. Now this is equal, considering the formula for z, which was exponential to exponential of mu beta. This is mu n, and I have a mu and then a beta, which is kBt, the first term. The second term is the logarithm of integral q p for number of particles equal to the average of n of e to the minus beta e. Okay. Now, what is this function here? This is the canonical partition function. Apart from normalization that I have not introduced, but one can introduce from the beginning, but it's not very important. But this is just the canonical partition function now, because I'm computing an integral at fixed number of particles. Now it's fixed, and it is equal to this number, average of n, and I'm integrating over dq dp e to the minus beta e. So this is just the canonical partition function. Is the canonical partition function for a system with average particles. Okay. Therefore, the log of the grand canonical partition function now can be written as follows. So this is mu divided by kBt, and here I have n, plus the log of the canonical partition function, z of zc, which was the canonical partition function. Okay. Now it's almost done in the sense that remember that z was e to the minus beta a, where a was the Helmholtz free energy. And G, the grand canonical partition function, was e to the minus beta, the grand potential. So when I do this, I get that minus beta omega here is equal to mu beta, if you want, is kBt, 1 over kBt is just beta, the average number of particles, which is n, minus beta minus beta A, which is the almost free energy. Okay, so I can remove this minus and this beta, and omega now is equal to E minus mu and average. Okay, I'm almost done in the sense that now what I need to do is to remember, well, first of all, in order to make a connection with thermodynamics, let me just, now we are in thermodynamics, okay? So basically, this must be considered in thermodynamics and always as a sort of average, as in the case of the internal energy, which is a thermodynamical quantity, and we know that it is an average. So let me substitute in thermodynamics. We are not always saying that, let me be more clear, in thermodynamics, we say that U is the average of E, and we use U in the formula. Okay, so now I have no symbol for basically also the books do not use a different symbol for that. So the average of E is internal energy, the average of N is just called N. Okay, but just that we know among each other that it is a thermodynamical quantity. Okay, so let me just rename the average of N as N, as the average of E was U. Okay, so problem of notation that I don't find in any books how it is solved. Okay, but it will not generate any confusion. Okay, so now we are in thermodynamics, and this must be considered as a thermodynamical quantity which can fluctuate. Of course, the fluctuations are very small, but okay. Whereas within statistical mechanics, this is a quantity on which we are summing. We are computing average. We are computing also fluctuations. Okay, so in thermodynamics, it's just and must be considered as a thermodynamical variable. So therefore, now since we are doing thermodynamics, let me just write this as follows. Let me also remember that another formula that was the following: G, which was the Gibbs potential, it was the product of mu times N. And we had also another equation that we derived, which is a fundamental equation saying that U is equal to Ts. Well, actually, this may be not even useful in this case, but okay, let me write it down. Plus mu N, just to, and also that G is also equal to A plus P times the volume. Okay, so those are the thermodynamical relations that we derived. And now you see that if I take A minus mu N, is just minus PB. So I get this relation from here, A minus mu N, which is omega, but A minus mu N is minus PB. Therefore, omega, so the ground potential is nothing but the product of the pressure times the volume. So it's nothing new, basically. Okay. So this is the ground potential. Ground potential. So this quantity is basically a thermodynamical quantity that we have already seen. So therefore, now we are ready to write the two equations that are needed in the ground canonical ensemble in order to connect microphysics with thermodynamics, which are the following. Since the grand canonical partition function was e to the minus beta omega, then you see that if I do the log of this quantity, and well, let me do the log of this quantity, log of t is minus beta omega, which is equal, by using this, is PV to the minus that drops. You just divide by KBT. Okay, so you have the first equation that tells me that PV divided by KBT is equal to the logarithm of the grand canonical partition function. And the second equation is basically will provide the equation of state, and we will apply it for ideal gas, just to check if our calculations are correct. And the second equation is that N, which in statistical mechanics is an average. I will put average of N. In thermodynamics is just N, and we know that this is a thermodynamical variable that can fluctuate, and it was derived as Z derivative with respect to Z of the logarithm of the grand canonical partition function. Okay, so those are the two equations in the grand canonical ensemble that allows you to find the link between microphysics, which is inside here, and the thermodynamics, which is instead here. Okay, and those relations will be used also in the case of the statistics, the quantum statistics, because they are particularly useful also in that case. Okay. Indeed, if you want, this is basically the relations that provides the equation of state. Whereas this equation here is the link between N and hidden here the chemical potential. So this is the relation between N and mu, which is the chemical potential. Okay. Good. So now let me see what happens in the case of ideal gas. Let me see what happens in this case. Vediamo come l'ho fatto. Actually, in this case, I can even compute Z of G in the following way. So by also summing over N, because calculations in this case are analytical, this was Z of N times the canonical partition function. This is equal to N0 to plus infinity of Z to the power of N, and the canonical partition function for the ideal gas was derived to be 1 over N factorial. Then I have the volume and lambda cubed to the power of N. Okay, for the ideal gas. And this is equal to the sum and 0 to plus infinity of 1 divided by n factorial z v lambda cube to the power of n. And now we know the sum of this series because it's just the exponential. Okay. This is the exponential of z v divided by lambda cubed. Okay. And this is the z of g that can be computed analytically without any approximation for the ideal gas, and the relation between z, so Vg is basically this quantity here. Okay. Therefore, the logarithm of this function here, the grand canonical partition function, is z v divided by lambda cubed. Okay. Remove maybe this. And by using equation 2, if I do the derivative of, if I do the derivative with respect to z of the log, I just get b divided by lambda cubed, and then I multiply it by z. Therefore, by using 2, n is just equal to z v divided by lambda cubed. Okay. But this was also, so basically you see that the log and n are the same, twice the same quantity. Okay. So zv divided by lambda cube is the log of the canonical partition function, which is pv divided by kbt, which is also n. Therefore, I conclude that indeed pv divided by kbt is just n, which is indeed the ideal gas equation of state. Okay. These calculations are, in this case, are analytical, and there's no approximation. I can compute the sum over n. And by using these two equations, which are the equations one has to remember for, one has to remember those equations for dealing with the grand canonical ensemble, we derive the equation of state of the ideal gas that was derived already before. Maybe we can do another thing here, another check, which comes from here, because as I said before, this relation here is the link between n and mu. And indeed, it works in the following way. Let me take this equation here. Maybe I remove this. This was just a check. Let's do another check. So from this equation, I get that this is the density times lambda cubed is equal to z. So density times lambda cubed is equal to z, and z was the exponential of mu beta. So now if I do the log of this quantity, log of n lambda cubed is equal to mu beta, and therefore mu is equal to kbt log of n lambda cubed. Okay, this was derived this relation between chemical potential and n, which is the total number of particles divided by the volume. This was derived for the first time in the microcanonical ensemble, if you want to compare. So we have done these two checks. We can reconstruct the equation of state of the ideal gas, which is the relation between pressure, volume, temperature, and number of particles. And also we have a simple way to compute the relation between chemical potential and N, that within the microcanonical ensemble was instead computed as a derivative of the entropy with respect to the number of particles. Okay? It was derived in a slightly different way. Okay, so this is okay, so it's finished. Now let me see what time is it. I think we can continue for a while. Now I want to discuss a little bit more the issue of fluctuations. So let me maybe start from this. So at some point we derived this quantity here, n squared average minus n average squared was kBt squared sorry, mi sono perso qualcosina qua. Okay, I will check in a moment. kBt squared, then there is a volume squared, and then there is a second derivative with respect to u squared of the logarithm of g. I think this is correct. This as in this case, yes. Yeah, okay, kBt squared, v squared. Okay, let me start from this point. Now, let me use the fact that we know now that PV is where we have shown this now, that PV divided by kBt is equal to the logarithm of the grand canonical partition function. And therefore, by using this relation, which is the equation of state relation, this turns out to be a volume that can be simplified, the temperature can be simplified, and then I have a kBt, not squared in this case, a volume that drops, so kBt divided by the volume, and a second derivative with respect to mu of the pressure. Okay. kBt volume, okay. Now I will try to compute this quantity here, the second derivative of the pressure with respect to the chemical potential, and then I will discuss all this. Now use the following fact that dP is a relation that we derived during the part of thermodynamics, is equal to S dT plus n mu, see thermodynamics, where S is the entropy density, more or less, is the entropy divided by the volume, and N is the usual capital N divided by the volume. Therefore, from this relation, I see that the first derivative of P with respect to mu at fixed temperature is equal to the density. And here, although it was hidden somehow, I'm not deriving, I'm keeping fixed the temperature, because indeed, when I derive with respect to mu, I'm considering T to be constant, okay? So dP mu at constant temperature is the density. Now I need to do another derivative. So the second derivative of P with respect to mu, again at fixed temperature, is N. So it's the derivative of N with respect to mu at fixed temperature. Okay. And now let's do the following trick. Let's write this derivative as dN dP, fixed temperature, dP dN fixed temperature. And now let me introduce this quantity that will be useful in a moment. Let me introduce the specific volume, which is small v equal to 1 divided by n. It's called specific volume. Now, in terms of the specific volume, now this quantity is, I'm getting lost, dN dP at fixed tac. And this is equal to dP d mu is equal to n. Sorry, I'm coming. So this is the n d mu, okay, and here I was n.
I guess there should be a mu.
Yeah, indeed, I lost the mu at some point. Exactly. I think I lost the mu here, no? So this is the n d mu, and here I have dP, and here I have a mu. Aspettate un attimo, mi sono perso un attimo questa cosa. So this is okay, dN d mu at fixed temperature. Then I do dN dP. Here I lost the mu, right? Okay, thanks. Now, yeah, I use this again. dP d mu is equal to n. Therefore, this n times dN dP at fixed temperature. Okay, now it's better. Definitely better. Now, n is 1 over the specific volume. So I have 1 divided by v, derivative with respect to p of 1 divided by v at fixed temperature. And I have almost done, because now this is equal to, when I derive 1 over v over with respect to pressure, I get minus 1 over v squared times the derivative of the specific volume with respect to the pressure. So I get 1 over minus 1 over v to the power of 3 derivative of the specific volume with respect to the pressure at fixed temperature. Okay. And this quantity here, what was this quantity? Was this quantity here. So it's the second derivative of the pressure with respect to the square. Now, let me introduce a quantity that maybe we had introduced already, which is the isothermal compressibility, Kt, which is minus 1 over the specific volume times derivative of the specific volume with respect to the pressure at fixed temperature. This quantity is called isothermal compressibility. With a minus, and you will see why there is a minus, but I think we have introduced already this quantity somewhere. And therefore, this is equal to 1 over V squared times the Kt, the thermal compressibility, the isothermal compressibility. Okay. Good. Kt divided by V squared. So this second derivative of pressure with respect to mu at the end is this quantity here. It's Kt, the isothermal compressibility, divided by the specific volume squared. And now let me come back to the fluctuations. So we said that n squared minus n average squared was equal to kBt divided by the volume. And here there was a second derivative of the pressure with respect to the chemical potential, which now we know is Kt divided by small v squared. Okay. Now this is also equal to, coming back to, well, since V is 1 over n, I can interpret 1 over n as actually, when coming back to statistical mechanics, 1 over the average of n. Okay, so in thermodynamics, we do not write averages because they are not ensemble. When connecting statistical mechanics with thermodynamics, and here is what I'm doing here, what is V here, or what is n here is just the average of n. Okay, so then this quantity is equal to kBt divided by the volume, K thermal, and here we have an n average squared, because this is 1 over P, the specific volume squared. Almost done, I'm almost done. So then I can put this here and see what happens. So if I do n squared minus average n squared divided by n squared, I get a kBt volume and Kt. kBt divided by volume and Kt. Okay. Where you see again the suppression with the volume that I have of the fluctuation, but only in the thermodynamical case, in the thermodynamical limits, and only in the case in which the isothermal compressibility is finite. So if Kt is finite and in the thermodynamical limit, we see that fluctuations are suppressed as 1 over volume. No? That was what I said before, although in the previous case I was using a more empirical argument that was telling that the logarithm of the grand canonical partition function must be an extensive variable, and therefore it must scale as the number of particles. Now here I can make more precise statements, in the sense that if I do the thermodynamical limit and KT is finite, then it's fine, in the sense that the fluctuations are very much suppressed as 1 over the volume. But for the case in which KT is not finite, if KT diverges, then I have a problem, in the sense that I can have macroscopic fluctuations. In which situation I have a divergence of KT? Well, this occurs when we have a second order phase transition, because you remember the isotherms of the van der Waals gas, they were done like follows. It was this, and then it was this. Okay. Now, this isothermal corresponds to T equal to Tc, because the critical temperature, and here I have a point, which is the critical point, at the critical point, I have the derivative of P with respect to the volume at fixed temperature, you see from here, is equal to 0. And this is just the inverse of the isothermal compressibility, which then diverges. It is diverges. Okay, so now in this case, the ratio between these quantities that is divergent and the volume can be finite. Okay, so I can have a macroscopic fluctuation of the density, which is macroscopic and then indeed can be seen. And this is actually the case when you are close to a second order phase transition, which is this point here. You have macroscopic fluctuations of the densities. Let me write it down here. Close to the critical point. We have macroscopic fluctuations. To something that can be seen. And these macroscopic fluctuations leads to some phenomena, as for instance critical opalescence, that you can critical opalescence. You can see, I think there are some movies also on YouTube in which you see that if you increase the temperature of a certain quantity, a certain material, which is transparent, and you move close to the critical point, then the macroscopic fluctuation of the density provides a finite opalescence to this material. Okay, so what we are describing here, what we are saying here is that the fluctuations usually are basically in the thermodynamical limit suppressed, but for the case in which we have a second order phase transition, because at that point we have to be careful. We have to be careful in the sense that in that case, since the isothermal compressibility is divergent, then the fluctuations are no more suppressed. Now, let me make another comment before I stop. Now we found that n squared minus n average squared divided by this quantity and average squared is equal to kBt divided by the volume times the isothermal compressibility. And previously, we also derived that if I do E squared average in the canonical ensemble, this was derived, minus E average squared was kBt squared, with the square only on T, times the specific heat, well, times the heat capacity, actually. Those are two examples of fluctuations dissipation relations, they are called. Or theorems, if you want, fluctuation dissipation theorem, in which on the left-hand side we have a fluctuation of a certain quantity, here the density and here is the energy, and on the right-hand side we have some quantities, the isothermal compressibility and the specific heat, which are related to derivatives of thermodynamical variables. Those are called fluctuation dissipation relation that we will see also maybe at the end of the course when doing the Einstein relation for random walk, etc. What is important to stress here is the following. The divergence of KT, and this is just only one comment that I will do on that, but something that you must remember for your life, in a sense. The divergence of KT is due to the thermodynamical limit. Divergence of KT at the critical point. This is something that I will not prove. One can try to do it. I will not do it. So it's due to the fact that I will send at some point we need to send n and d to plus infinity. Actually, when writing this relation PV kBt equal to logarithm of z of g, and the other relation that n what is equal to derivative of z of the log of z of g. Actually, when computing the log of the grand canonical partition function without assuming any thermodynamical limit, those are analytical functions, and therefore I will not have any singularity in the derivatives, because analytical functions are you can derive them infinite times, no? So here, without the assumption of n going to infinity and b going to infinity, no singularity. So if you want, this function here is analytical in its arguments. So I do not have any divergence of this. Therefore, at the end, I can conclude that actually this divergence is due to the thermodynamical limit that in finite systems, so in which the volume is finite and the number of particles is finite, I do not see this divergence. Okay, so in finite system, where n and d are large, but anyway finite, in principle, there are no divergences. And so, strictly speaking, no real second-order phase transition. Okay. So, to make maybe the connection more clear, the divergence was derived from the second derivative of the pressure with respect to mu, not because at some point we say that this second derivative of P with respect to mu was proportional to the isothermal compressibility, and this has a divergence. But actually what I'm saying here is that this function here, which is related to P, sorry, it's analytical. So actually, without doing the thermodynamical limit, I will add that all the derivatives of this quantity are actually finite. So in principle, there's no real second-order phase transition, so no divergence in finite system. Okay, so this is something I'm not proving; I'm just providing an argument, but it's important to remember because when looking at second-order phase transition in real systems, one has to be aware of the fact that, of course, one will not see any divergence. Okay, one will see something that goes. The isothermal compressibility explodes. Of course, can become very large, but there is no real divergence. Of course, this is an artifact of the thermodynamical limit. Okay. Now let me conclude. Or maybe we stop for a while because it's 12, okay, it's 10 past 12, so maybe we stop for 5 minutes. It's better. So let's stop. Okay.
Se si può uscire o essere
Io penso che non si possa, cioè, non là perché siamo già queste cose le dovete chiedere alla Giuti, chiedete a lei, che sennò poi se io posso uscire se la prende con me. Chiedete a lei. Ok, facciamo ancora una cosina sulla Grand Canonical e poi passiamo alla Quantum Statistics. La cosa che voglio fare è ricavare, perché sto scrivendo in italiano? Perché sto parlando in italiano? I want to derive a formula for the distribution function, the Grand Canonical distribution function, which was rho of n in E for ideal gas, the case of the ideal gas. And we will see that this is a Poisson distribution. Now, okay, some relations that we already derived are the following. We say that for the ideal gas, the Grand Canonical partition function is E to Z V divided by lambda cubed. This was derived. And we also say that the average number of particles is equal to Z V divided by lambda cubed. Okay, and I think this is what I need. Now, blah, blah, blah. So the rho is equal, by definition, to Z to the power of n, the canonical partition function Z of C at a certain value n, divided by Z G, which was the normalization, if you want. Now, let me see. So this here in the denominator becomes e to the minus ZB divided by lambda cubed, which is also e to the minus the average of n. So actually, this is e to the minus the average of n. And then I have z to the power of n. And now I just remember which is the canonical partition function, which was v to the power of n, lambda to the power of 3n, and then I have 1 divided by n factorial, which is equal to 1 divided by n factorial, e to the minus the average of n, and then I have zv divided by lambda cubed to the power of n. But this quantity again is the average of n to the power of n. So then it is equal to 1 divided by n factorial e to the minus the average of n times the average of n to the power of n. And I think that's it. This is rho. Now this distribution, which is the Grand Canonical distribution function or the Grand Canonical Ensemble, if you want, for the ideal gas, is basically a Poisson distribution. Poisson distribution. And the Poisson distribution has the following shape. So let me write the general formula, P, Poisson distribution, Poisson. Here così Poisson, non era così Poisson. Is equal to lambda to the power of n divided by n factorial and e to the minus lambda, where lambda is the average of the distribution, and the variance for a Poisson distribution is still equal to lambda. When these are a result of probability theory that you might remember from the first year, otherwise you can have a look, or you can try to prove it. Okay? So the Poisson distribution tells you that if something occurs with an average lambda, and you ask yourself if this event will occur n times, so the probability scales as well, is equal to lambda to the power of n e to the minus lambda divided by n factorial. Okay. Is the distribution for rare events. Okay. And so something that one could remember from the Poisson distribution is that the average is lambda and the variance is still lambda. Okay. Therefore, when I apply this result to our Poisson distribution, I can say that the variance minus n squared, so yeah, is basically equal to the average, applying this result here. And therefore, if I now compute the fractional fluctuation, which will be equal to n average minus n average squared divided by n squared, and maybe we can put a square root. Now, in the numerator, I have something that is actually square root of the average of n, for what I said here, whereas in the denominator, I have the average of n squared. So this simplify with this, right? And therefore, the fractional fluctuation scales as 1 over square root of the average of n divided by b, that's in here. So the fractional fluctuation scales as 1 over the square root of the average of n, which of course again is going to 0 and going to infinity. So it's another way to see that fluctuations are very much suppressed for macroscopic systems. No? And now we know that the fluctuation of the number of particles is a Poisson distribution. So the way these fluctuations occur, so the probability is provided by a Poisson distribution, which is something that cannot be derived, of course, in thermodynamics, but comes from only statistical mechanics. It's another argument to say that fluctuations are suppressed. Okay, so now that's all for what concerns classical statistical mechanics. Now we have to do quantum statistical mechanics. And at some point, we will arrive at the distribution of the Fermi-Dirac and Bose-Einstein distributions that you have seen already, of course. But I'm not sure, I don't know exactly how those distributions were derived. We will derive them in the Grand Canonical Ensemble, and we will choose a couple of applications that I'm almost sure that you have not done yet. For instance, the Bose-Einstein condensation, because usually this is not done the previous years. Okay, but at some point you will tell me. Anyway. So what we have to do now is to introduce quantum statistical physics. statistical mechanics. Si vede ancora, sì. Now, what are the differences with respect to classical mechanics? We cannot use the phase space anymore. This is forbidden because the commutation relation between Q and P is different from zero, no? So I cannot describe a system in terms of a phase space. Okay, so I will not have integrals over coordinates and momenta because they are not, these variables do not commute. So there's no meaning of doing that. Okay, they are observables. So what I do instead of phase space, I will have to work in a Hilbert space. Which is the Hilbert space of the states of the system. Okay, so no phase space anymore, we have a Hilbert space. Another difference with respect to the classical case is the fact that I cannot distinguish particles. Well, actually, this is a point that was already somehow useful and important also in classical statistical mechanics, which was somehow put inside the system, inside the theory, by requiring that the entropy was an extensive variable, okay, the Boltzmann counting. But here you have to take into account the fact that particles, well, the fact that I have identical particles, okay? Identical particles, which means that the wave function must be symmetric or antisymmetric with respect to the exchange of particles, okay? Wave function. Symmetric or anti-symmetric with respect to the exchange of particles. With respect to the exchange of particles. Okay. This is something that you know already, so that's why I'm running. Then the question is, we have already seen that actually some corrections due to quantum physics come and are mandatory also in the classical case for what concern, for instance, the Boltzmann counting. That was important. But now we can ask ourselves, which is the situation in which we cannot avoid to use quantum statistics, and we cannot use classical statistical physics. Well, we have already introduced a quantity that plays the role of, let's say, that allows us to switch from a classical description to a quantum description, which is the thermal de Broglie wavelength. The thermal de Broglie wavelength was equal to h divided by 2 pi m kVt, okay, which can be also written, and I'm doing that just because I would like to use natural units. It can be written as follows: square roots of h bar squared times 2 pi, and here I have m kVt, okay, because h bar is h divided by 2 pi. I get the 2 pi here, and the 2 pi there. Interesting. And as you might remember, at some point in the canonical ensemble, in the grand canonical ensemble, the micro canonical ensemble, Well, for instance, in the relation between mu and the density, we just derived this before again. There was the product of n lambda cubed. In the grand canonical, well, in the canonical ensemble, we have that the z of c was 1 divided by n factorial. And here what we have v to the power of n divided by lambda cubed, to the power of 3n. And for instance, so again, here you have to compare a volume with the lambda 3n, giusto, no? So this was equal to 1 divided by n factorial and v divided by lambda cubed to the power of n. So if I introduce up and before n to the power of n, again I get the density times lambda cubed. In any case, what I have to compare is always the scale of lambda and the scale, typical scale of the macroscopic system, no? So basically, quantum mechanics starts to play a role important or necessary when n lambda cubed equal to 1, which means, if you want, that the typical distance between the two particles is similar to the distance, or well, is similar to the thermal de Broglie wavelength. Okay, so the average system, average distance between two particles is close to the thermal de Broglie wavelength. Of course, in this situation, so for a large density, large enough density system, we have to take into account of quantum mechanics. Okay, if I have a system which has a very small density, that means that particles are far away from each other, so I have no overlap of the wave function, basically, if you want. But if the density is large and the critical condition is the following, basically in that case I have to take into account of quantum mechanics. So let's try to make an estimate for a real system, macroscopic system, to see if we need to introduce or not quantum mechanics. And let's make a typical example, which is the gas of electrons at room temperature. So let's consider a gas of electrons at room temperature, which is 300 Kelvin, which in terms of MeV or energy scale is this famous 26 millielectron volt with 0.0026 electron volt. Okay. You might remember this number, or you might remember the fact that 1 MeV corresponds more or less to 10 to 10 Kelvin. Okay. Or you can remember that 300 Kelvin is equal to this number here. It's up to you. Or remember that 1 MeV is close to 10 to 10 Kelvin. Okay. This is the conversion factor that you can try to remember in order to see what are the scales. So now the lambda can be estimated by using the previous formula. Let's make the lambda squared, which is equal to natural units, of course. I had the 2 pi and h squared, which is 1 in natural units, and then I have, in the denominator, I had the product of the mass and the temperature. And the mass is 0.5 MeV for electrons, and the temperature is this number here. So it's 0.26 electron volt. And now if you do the calculation, of course, the lambda squared has a dimension of 1 over energy squared. And if you want to convert this into a length scale, you must at some point multiply by h bar c, which is equal to 200 MeV times Fermi. Okay? So if you multiply this 200 MeV Fermi to the power of 2, then you get a length scale as you like. Okay? Now you do the calculation, and lambda comes out to be those numbers, 4 times 10 to the minus 7 centimeter. Okay, so this is the thermal de Broglie wavelength of a gas or electrons at room temperature. Okay, now let's consider instead the density 1 over n equal to, just to put real, well, macroscopic and reasonable numbers, let me put this as 10 to the minus 22 centimeter squared, which means that in 1 centimeter cubed, I have 10 to 22 particles, which is more or less the order of magnitude of the Avogadro number. No? You take the cubic square of this, and then you get the typical distance, the distance between the particles, is of the order of 5 times 10 to the minus 8 centimeter. Okay, for these numbers, these are basically, well, reasonable numbers. Okay, so the Avogadro number and a scale of 1 centimeter. And so you see that this number here and this number here are actually more or less of the same order of magnitude. Actually, for the example that I've taken, is even smaller than this one. And so therefore, in this situation, for a gas of electrons at room temperature, I need, well, I'm forced already to use quantum mechanics. Okay, so even at t equals 0, and for electrons, Qm is necessary. And also another pen is necessary at this point. Vediamo cosa viene qua. Il blu l'abbiamo provato. No, il blu è ritornato vivo, forse. And indeed, you might remember that a gas of electrons in a metal is considered to be a degenerate gas. I think you have done this before. So quantum mechanics plays a major role also at room temperature for a gas of electrons. Sono 46, okay. Good. So before trying to build up the statistical ensemble, well, basically what we would like to do is to translate the language that we have used for classical statistical mechanics to quantum statistical mechanics. Instead of phase space, we will work in a Hilbert space. Instead of canonical, grand canonical, classical ensemble, we will derive a similar ensemble but in quantum mechanics. Now, the thing that those ensembles are expressed in quantum statistical mechanics in terms of density matrices. And I'm not sure how much you know about density, the density matrix. You know that the thesis, you have done the thesis on that.
Density matrix. Okay.
Matrice densità. Okay. You know, maybe the other are not very familiar with that. Okay. So the density matrix is a tool of quantum mechanics that is particularly useful also in statistical mechanics, because it allows us to distinguish among classical mixture of particles with different properties and a quantum superposition of for instance, spin. Okay, so the density matrix is the language that at the end will be used in order to make possible to write the ensemble in quantum statistical mechanics. So those ensembles are actually density matrices. Okay, and so for the rest of the hour, which is almost 10 minutes, we'll try to introduce this tool, because at the end it will be useful for doing quantum statistical mechanics. Okay, so suppose that we have we work in a Hilbert space now, and we have n possible states. For an observable with n possible eigenvalues. This can be done also for an observable with infinite, in principle, with infinite eigenvalues. Okay, but let's consider the case in which we have n possible states, each one with a probability Wi, probability of being occupied. Occupation of state, come li ho indicati, alpha. So those states are called alpha I, where I runs from 1 to n, and Wi is the probability of occupation, or the probability to find a particle in such a state. Okay? Now the density matrix is defined as follows. So rho is the density matrix, is by definition is the sum from I1 to n of the probability of occupation of a certain state alpha times the projector. Okay. Is the definition of the density matrix, with the constraint that the sum from I to n of Wi is equal to 1, because those are probabilities. Okay. So now to make an example of this, suppose that you have a sample of particles in which 50% of them are with spin up and 50% are with spin down. Okay. So with W1 equals 0.5 probability of spin up, if you think about a system with polarized particles, and W2 equals 0.5 with spin down. Okay. Then in this case, the density matrix is basically 1/2, that's indicated with plus the spin up, plus 1/2, minus. Okay, this is just the density matrix. Now, this situation is very different actually from the situation in which I have a superposition of states. So here what I'm saying is that those particles are polarized, and some of them, well, 50% of them have spin up and 50% of them have spin down. It's a different situation with respect to this situation in which I have a sample of particles that are instead in a state all in a state C, which is provided by the linear superposition of a plus and minus. Okay? Because actually, if this is a polarity, so if this is spin of, suppose that this over the Z, suppose spin of Z axis. Actually, a system with these of particles in this state are always, well, all of them are in the spin x plus. Okay, so a plus in the x direction. Okay, so basically, if you have all particles with the spin plus, but in the x direction, you decompose the state into the states, well, into the eigenstates of the spin of the z component of the spin, and you get this result. Okay, this was done in quantum mechanics. Okay, but now what I want to remark is that this situation is very different from this, because in this case we are talking about a mixture, which is a classical mixture of particles, in which some of them are with spin up in the z direction, and some of them are in the minus direction, again along z. Whereas in this case, I have a linear superposition of plus and minus. Okay, when I make a measurement, of course, the probability to get 1/2 plus. So the probability of getting plus and the probability of getting minus is again 1/2, as in this case. But this is a mixture of state, which is a pure state, whereas this is a classical mixture of states, which is something which is more similar to a classical mixture. Okay. Now this will be formalized as follows, actually, because now in this case the density matrix is this structure here, whereas in this case the density matrix rho is just C, which is equal, let's make the calculation, is equal to 1 divided by square root of 2, here we have a plus minus times 1 square root of 2, and here we have a plus and minus there. Okay. And you see now that this is different, no? Because here I have 1/2, then I have here a plus minus, plus minus plus, sorry for the, and here I have a minus minus. And you see that the structure of the density matrix now is very different. This is the one for a pure state, which is called pure state. And this is the case instead of a classical mixture. Indeed, to make the situation even more evident, the difference between these two situations, let's derive indeed really the matrix expression of those two cases. And to do that, we just need to project. So let's consider the structure here. Rho is equal to 1/2 plus 1/2 minus minus. can write a matrix form out of this by just projecting, no? So you make the fai panini, no? Questo in order to find the matrix element, no? Il primo panino, the first panino, the first hot dog becomes 1/2. No, this is 1/2. The second is 0. This is 0. This is 1/2. Right? Is it correct? Okay. So then the matrix form of this operator is just 1/2, 0, 0, 1/2. Whereas in the second case, if you do the same calculation, so you compute, vediamo se il vostro si è ripreso intanto, magari si è riposato, and I need to stop for a moment, and I need to stop in a few minutes. In this situation, you do the same, so you do all the combination, and you will get a structure that is the following in this case. Rho is equal to 1/2 here, 1/2 here, 1/2 here. Okay. It's a different structure. One can show, dove che sto? Qua, 4, 5. One can show that in general, this maybe we will prove it next time. The trace of rho is equal to 1, and this is valid in general. And you see already from those two matrices, no? If you do the trace of rho, this 1/2 plus 1/2 is 1, and is also 1/2 plus 1/2. So in general, the trace of rho is equal to 1. That's the matrix. Whereas if you do the trace of rho squared, you get to 1 just in the case of a pure state. Whereas you have the trace of rho squared less than 1 for classical mixture. By classical mixture or admixture of states, I mean that I do not have a superposition in quantum mechanics. I just have that if I have 10 particles, 50% of them are with spin up, 50% are with spin down. These are classical, so those are particles are already polarized. Whereas in this case, by using the previous example, all of the particles are in a linear superposition of plus and minus in the z direction, which is a very different situation because actually those particles are actually polarized in another direction, which is x plus in the case of the spin. Okay, but when doing a measurement, of course, in this case, I will get that 50% will have spin up, 50% will have spin down. And also in this case, I will have 50% spin up and 50% spin down, if I measure along the z direction. If I decide to measure along another direction, then the results are completely different. Because if I decide then to measure along the x direction or another angle, the result should be completely different. Okay. And so now the thing is that at some point, we would like to reconstruct statistical mechanics and to try to be in situation like this one. So a density matrix which represents a classical mixture of states instead of a linear, instead of a ensemble of pure states. Okay, we will continue next time. Bye bye.
Arrivederci, prof.
Arrivederci.
Arrivederci.